So when we say we are evaluating a machine learning model, what do we really mean by this? So let's move on and see what do we mean by evaluating model and how do we do it? What are the different methods that are available? First and foremost, as we know that when we talk of machining, so especially the supervised one, we have the training and the testing. So once you train your system, so you actually try to generate what we call the hypothesis function. We want to get the hypothesis function. So which is actually referred to as H. So every machine learning algorithm has its own hypothesis space, big H, from where you can have several possibilities, H1, H2. So you have to search for data. If you give me data one, it might be H1. Let's say this is neural network, for example, I'm using. So this is the hypothesis space for neural network. There are so many possibilities inside that space. It could be H1. Maybe for data one, it could be H3 that work for it, remembering the principle of let the data speak. So you might have another data, it might be H10, because there are different possibilities you can get inside that H. However, once you train, you expose the training data set to the system, and then it trains itself. So we generate the H given X that you are providing, which is the input, and theta is the parameter. See, there are some parameters that we talk of parameter optimization. If you remember when we talk about how to write machine learning research papers. So you have to describe the parameter. So given this hypothesis function that you have derived, this is the original given data. This is the original output, the actual output given to you. So we need to find the difference between. So what is the output from the trained model and compared to the original actual values? Let's say I'm trying to predict the score of a student in the final exam. So after predicting, I need to, okay, this is the assumed one, the actual one. We are using historical data. Okay. Now, like I was saying, so once we have the training, the system is already trained, we have the H. So we need to see how is this H of X given theta, how is it doing? So this input we have used in training, so we give it into it, and then we say, okay, take the values. Can you predict this, maybe sample one? Are you able to predict the actual value? We compare it with the original value. So this is why we say that we need to calculate the empirical error function for the model we have developed. So we are going to find the summation of it. The summation is what we need to calculate to be able to know that, okay, how is this particular model, how is it doing at the appropriate time? Now, so if we are dealing with regression problem, we are going to be talking about distance, that is the squared error. So if H and F, they are real valued. So if you are predicting actual values, so we'll be talking of that is regression, we'll be calculating the distance. Otherwise, we'll be talking of delta function. If H and F are categorical, which is classification. So, however, the question has always been, how do we divide our data? How do we really check this particular evaluation? This what we are doing is that we want to evaluate the machine learning model. So how do we check it? How are we sure that we are doing it the right way? That reminds us of about the very important hypothesis behind machine learning itself, which is a inductive learning hypothesis, which state that if the hypothesis works for enough data, then it will work. Then it will work on if an hypothesis work on enough data, then it will work on new examples. So the question is so which data is enough? So it means we need to use some data to check our hypothesis if it's actually working. So if it works on enough data, we are hopeful that when we have new data set that we have never seen before, then it should be able to work on it. This is a principle that is very, very important, which means when we are building model, we need to assign portion of our data to be used for the training so that we'll be able to have this condition if the hypothesis works for enough data. So the portion A is going to be the one we call the training set, In the training set, the unique thing is that we have the inputs, X1, X2, and X3. Let's say we have three features. And we also have the target value. So we are going to give out the value of X1, X2, X3 to our system, and we show the system why. So when you have a student with this attribute, with this attribute, with this attribute, this student actually score 60%. When you have another student with this attribute, they got 75. So we give different things like this to the system to understand. Once it's well understood, we now check it again. Since we gave you this, you understand the output, that is the training process. We still give the same input back to the system to check what you have seen before. Are you able to predict it with acceptable level of correctness? So the same data set we have used for the training, we try to, that's what we call the training performance. We need to check the performance on the training. We have shown you this, and you have declared, okay, I'm done with my training. Okay, let me test you on what you have been trained on. Let me test you on what you have been trained on. Are you able to identify what I showed you before? This is the essence of training performance checking. However, as I've always said, training performance is not the ultimate. You might have 99% training performance, but on the testing set is getting 40%. That is unacceptable, and that is called what we call overfitting. We described that also before. So that is overfitting. It means the system memorized the training set because it has seen the output before, it was able to memorize it. Our target is to have a system that will perform on the testing set of data that it has never seen before. Then we want to see how it's going to perform. Now, so once we check that, once we check the performance for training set and it's reasonable, then we go ahead on the testing set. This is why the hypothesis is very important. If the hypothesis works for enough data, that is, if the train model you have generated, if it works on that enough data, which is the training set, then hopefully it's going to work on new examples that are yet to be seen. Now, this brought the concept of generalization. This is what we're saying. See, this is the training set. We know the label. So we give each of these to the machine and we say, this is an apple, this is seed, this is tomato. So we let the system get trained as much as possible. That's the training idea, the idea of the training. Now, then we have the hidden data set, which we call the test set. The machine learning is made not to know the output of this one. You can see here that this is an apple, this is tomato, these are different animals. However, the machine learning model doesn't know about these. That is why we call it. Now, we now want to check if the machine learning is exposed to this set of training sets, and then later we also test the machine learning on the same training set that it has seen before. The labels are known. We try to ask the machine, okay, what is this one? All right, although it saw it before, we want to see if it's able to recognize this once again. Once that is done, that is okay. We don't call that generalization. Generalization now is the model that we have trained on this data. Can we now make that particular model to work on data set that has never been exposed to the machine, to the algorithm itself? So this is where the concept of generalization comes in. So we want the system to be able to generalize to unseen data. And that's what your client wants, actually. Your client wants you to build a model for the industry that such a way that if it's so good, we can always use it on our new data set that can arrive at any point in time. So now, so the idea of generalization is how well does a learned model generalize from the data it was trained on to a new test set. So this is the idea of generalization that we're talking about. Now, so to check the generalization, so there are different ways of dividing your data. See, how do you check generalization abilities of model? See, so to estimate the generalization error, we need data unseen. You need unseen data to check. Data that's never been exposed to the system. So during the training. Therefore, we split the data as there are two main options. The first option is the one we call the holdout method. Holdout method. This is where you divide your data into two or into three places. You divide into data into 2 or 3 places. We call them holdout method. And then the second one is what we call the n-fold cross-validation. N-fold cross-validation. So we take them one after the other as we move on, inshallah. So we actually use resampling, that is n-fold cross-validation, when the data set is few. You see, when the data samples, there are very few data samples available. If you have huge data, this is recommended for you. But a situation whereby you have very few data set, depending on the area, and then the question is how much of data is few? It depends on your area of interest, area of application you are considering. In some fields of study, in fact, having 1,000 will be samples will be considered small sample data, because people used to have like 50,000 for their training and testing process. So if you have 1,000 in that place, they will see you as very small. But there are some other areas whereby even to get 200, it's like a huge success. So it depends on the area you are dealing with. So we deal with it according to the area you have. But then if data is small, usually people prefer that you go for the n-fold. And then it also depends on other things we're going to clarify later. Like if you are working on a project that someone did before, maybe there's a published paper where they use n-fold cross-validation. So if you're going to work on the same research paper to improve the result, for you to be able to compare your work with the earlier researcher, it's good for you to use the same partitioning method he has used. Otherwise, there will not be basis for you to compare your work with the work. Somebody divided data based on holdout, and then you divided your own using n-fold, then you cannot be comparing the two because you are using different approach for the division. However, if I am the one, I would rather implement the two. Since I'm comparing with the previous guy, he used n-fold. Maybe I felt that he's supposed to use the other method. Okay, I can implement the two methods. Implement n-fold cross-validation, and also implement holdout method. And then compare the one he used with your own that is similar to his, and then make further discussion regarding why you feel what you have developed as an additional partitioning method is the best one that will have been used. This is open for discussion in your result presentation. Now let's move back to the two different types. We said the holdout method and the n-fold. Now let's look at the holdout. Holdout has another two methods. Holdout is divided into two types again. So we have where you divide into three portions. We have training set. It could be 50%. It's not fixed, by the way. It could be, then you have another one, validation set, 25%, for example. Then you have another one, testing set. So we call it publication set, which is another 25%. So it means if you have like data set of 1,000, so you're going to use 500 for training, 250 for validation, another 250 for testing. Then the percentage also can change. I might decide to use 70% for training, 15, 15. I might decide to use 80%, then 10, then 10. So it depends. The second type is where you divide the data into only two portions. 75% training, 25% training, or 80% training, 20% testing, 90% training, 10% testing. To me, this is getting to the extreme. The data you want to use for testing is very small. So personally, I prefer to stop after 80 or 85. Though it's good for the data set, it's good. The more the training set, the better. However, we also want to make sure that the testing we are going to do is sufficient enough. So if the number of data set you want to use for testing is too small, then that could also lead to problem, as we are going to see later on. Now, in these two methods, either you divide into three or you divide into two. Both of them are acceptable. However, I have to clarify for us that there are a couple of people who believe that when you divide into only two, then you are going to do training using this one and then testing using this one. And maybe you check it again. If it's not working, you train the model more here and then come back for the testing. They are the opinion that it seems you are trying to tailor your model to understand the testing set, because if the testing set is not good, you go back again and do parameter optimization, and then you come back again and check the testing set. But however, note that there is no point at which you expose the system to the output of these testing sets. So this is why the proponents still say, even if you do that, there's nothing wrong with that. But sometimes you have a couple of people, especially reviewers, who are of strong opinion that, no, you have to use 3. And if your data set is small, then you cannot be talking of dividing into 3. So you might only be able to implement this. So either of the two, it should be fine. But then we have to be aware of some of the challenges that can come from people who want to review our work. However, the good news is that either this or this are acceptable, provided you make sure that you never expose this testing set to the training during the training procedure. Now, let's look at this one we call the infinite data. This is the holdout method. I just explained the holdout method. You just divided the data into 2, training or testing, or training, testing, and validation, as the case may be. Percentage of division could vary, 60, 40, 70, 30, or a host of others. So you have your training set, and then you have the validation test or the testing set, as the case may be. So, and then you divide your data appropriately. Now, here we say we train each model on the training data and then test each model on the validation side. I've seen someone made mistake. We developed 2 models, ANN, neural network, and decision tree. He trained this using n-fold cross validation, and then trained this using holdout, division into 70, 30. I said, no, you cannot compare 2 methods by subjecting them to different training procedure. And you're going to see the difference between the two and why you cannot be comparing them. Now, so these are just illustrative example. So you have your data. The first thing you divide into training and testing. So let's say you are using only 2 division. So you give it to you expose your training set to the algorithm to build a model. Okay. Once the model is built, then you have this testing set that you now supply. So this is why the training, you can see that the training set, the testing set never enters the building block. You don't use the testing set in the building block. Yeah, you only use the training set during the building process. So we can now use the testing set to check if the accuracy is acceptable to us or otherwise. So we check the prediction, if it's positive, this is negative, we compare it with. Of course, for the testing set, we as the developer, we have the answer. So we compare the answer to what the machine is predicting for us to see if it is correct to our satisfaction. However, during the training, the system was never allowed to have exposure to that testing set. In the case you want to have 3 division, like I said, we are still under holdout method. You want training, validation, and testing set. That's fine. So what happens? You divide your data into 2. The big chunk, like maybe 70, like 85% goes inside here. We call it model builder. So then the testing set is 10% outside. It's not even inside that particular area. So you have training set. So build to the model builder, you bet this your algorithm being built now to become a model. Like I explained one time, when you have algorithm plus data, in the training process, it generates what we call a model. So model is the outcome of the 2 when you mix them together in the appropriate manner. Now, you can see once you build the model, we have the validation set here, right inside there. So on getting into the building block, you also divide into 2 training set, test, validation set. So you use this to check. This is the validation set. This one didn't see the ones before. We want to check it. If it's okay, you can repeat as many times as possible. Finally, once you take the final model, yeah, this is my final model. Nothing to be done. No more tuning parameter. So you move in, out here, and then you now bring the big testing set. Sometimes this testing set could come new from the industry, from the client you are working for. So you bring it in and come and check. And then this is going to be the final evaluation. This is what we now determine what is the performance of our model. So this is, if you have enough data set, this is the method that everyone accepts as the best way to go in testing. However, if you see someone that doesn't have validation set separately, he only has training and testing, it is also okay. acceptable also to very big community of machine learning developers, though few, I call them few extreme positions, doesn't want to allow that. But there is a lot of logical interpretation that says that it is okay to do that. Yeah. That is if you divide it into 3, which I recommend for you if you have enough data set. Why not? So go for it. This can be compared. In fact, you can do this several times actually. Like one of the professor that they developed a machine learning model for, he was so surprised with the excellent accuracy, the excellently accurate result produced. Maybe he started doubting that maybe because I gave data to this guy, that's why they manipulated my work. He said, you come to my lab, I will give you new data. And then he there's okay, no problem, we show you how to do it, bring in your new data. Then he click in his own data, and he was surprised to get the very accurate result that the system was getting. So in such a case, usually we call it on-site testing in computing, in a software engineering. After we build the software, we call it, sometimes we call it acceptance set testing. Acceptance testing in software development. It's okay also for machine learning. Why not? Acceptance testing is when you build a software, you test it severally where it has been built in the software industry and software house. But when you want to deliver it to the client, you have to test it again. Sometimes client will bring its own real life data. You want to make sure the software is working. So in similar way, this could be comparable to that one. So because this testing set is totally outside the model building block. So these are the 2 methods when it comes to holdout method, where you divided data into 2. Now, a variant of it, slightly variant of it, is what we call repeated holdout method. Repeated holdout method. People decide to do this because sometimes there are some algorithms that we say they are not stable, like neural network. See, we say the holdout estimate can be made more reliable by repeating the process with different subsamples. See, there are situations whereby you want to repeat the process several times. You set up a loop. So I divide my data into 70 and then 30% testing. This is kept outside. So when I train, I predict, then I note down the result. I do it again another time, I know that the result. I keep doing that for 10 times. So I'm going to find the average of the 10 runs. Because sometimes like neural network, if you run it like one time, maybe you got 98%. Second time, you might get 96%. Another time, 97%. Because it's little variation could come, especially for those we call unstable classifier. Maybe the weight might be the one that is changing. The weight could be the one responsible for such change. So that's why we have this kind of, it's not very common, but sometimes people use it. We call repeated holdout. So you do the holdout, the partition to 2, training, testing, or 3 repeatedly, and then you find the average to see how it is actually going. So some people usually they randomize the data. So when you have training set, even that training set, you try to randomize once again when you introduce it again. So they do it different times, and they want to see, okay, how the data is going to perform on this. However, it is recommended that rather than doing repeated holdouts, okay, they recommended that why don't you use cross-validation, which is the second type that we say we are going to discuss. Why don't you just do cross-validation, or the one called n-fold cross-validation? So because it's the same thing you want to build, this is what is going to be similar to this. So when you partition your data, here they are saying, okay, partition is 70%, 30%. When you finish, partition it again, 70%, 30%. You do it again. So you keep partitioning it. So, which means some that were part of the testing set here, they can become part of training the second partition. This one is part of training, testing here. Next time it could be part of. So this is the idea of repeated holdout. So the proponent of this idea felt that, okay, let us give opportunity for every data set to be part of training so that we see how the output is going to be for the testing. Then the caveat is, this can lead to overlapping because sometimes even when you are randomly partitioning, some could be repeated also. So that why don't we all just go for cross-validation instead? But then this is also another proving method that people do use in checking or evaluating the performance of models. Now, to the n-fold cross-validation, which is often recommended when the data is not huge, because the idea of n-fold cross-validation, as we are going to see, is you are going to divide your data into certain number of portions. That's why I call it n-fold. N can be equal to 10. If your data is very small, your n actually can become 3. You see, your n can be 3, it can even be 2. So, but at least 3 is recommended. It doesn't have to be 10. That's why we call it n-fold. Those who choose the number of fold you want to use, and then you partition your data. Let's take, for example, this is full data set. This is the first partition. In the first partition, I'm going to use all this for training and only this portion for testing, or you call it validation. It's up to you. You can see that in the second partition, this was for training. This was what we use for testing. It's now part of the training set. It has moved to become part of training set. Part of this one has been cut out to become part of the validation set now. So we keep moving this window down until each partition is going to be used for testing the model at least one time. I'm going to show Imam. The procedure for cross-validation is to do this. Step 1, you split the data into k subset of equal size. Let's say I have 100 samples, and I want to use 10-fold cross-validation. So I split them into 10, and that's means I'm going to have 10, 10, 10, 10, 10 in each partition. So in each subset, in turn, is used for testing, and the remainder one used for training. Every time, if I'm going to use 10-fold, it means I'm going to train the model 10 times. So let me show you the practical example here. This is my data set. I've partitioned it to 10 places. This is 1, 2, 3, 4, up to 10. This one, let's say this one has like maybe 500. This one has 500. All of them 500. That means 10 times 500. That means I'm having like 5,000 data samples. So I divided to 10 places. I call this one fold 1, fold 2, fold 3, up to fold 10. So this is 10-fold now. So when I want to do the first training, so I'm going to train with all these data sets from here to the end. I combine them together. That's going to be 5,000 minus 500. That's going to be 4,500 for training. And I'm going to use this small portion for testing. And I will record the result. Maybe the result is 95%. I will record it down. I move to the second fold. You can see now, I'll bring this one back to the training fold. You can see this one now. This is for training. This is for training. See, what I used for testing before is now part of training. The one that was part of training is now part of, is what I'm going to use for testing. I'm going to use only this one for testing. This is called fold 2, and I'm going to record the result. Maybe I got 94%. So I keep shifting this particular window until I use the last partition here for testing, while every other one will be used for training. So this is called 10-fold cross-validation because I divide it into 10. It could be 5, it could be 3, it could be 7, it could be 6, as you want. So by the time I'm done with the last one, maybe I got like 98% here also, or any number. So I'm now going to find the average. The accuracy of this particular model is going to be, you sum together all the 10 folds, then divide the sum divided by 10 because it is 10-fold. That's going to give you the final result of your model. This is what we call 10-fold cross validation. Yeah. So like we said, the standard method is to use the 10-fold, divide into 10. So from experience, a lot of people believe so much in 10, but it's not compulsory. This extensive experiment have shown that this is the best choice to get an accurate estimate. Of course, this is opinion. So, but if the data is really, really slow, you can go for 3. I think one of the reasons also is that, when you divide data into 10, by virtue of 10, when you divide anything by 10, the division is usually easier compared to when you are dividing with any other number. And this is one of the secrets behind it. So now, and then stratification is also encouraged. What is stratified cross-validation? stratified cross validation is that when you divide the data into 10-fold, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you try to make sure that the classes are also evenly distributed. This is where stratify comes in, where stratification comes in. You try to make sure that it is correctly divided. So let's say I want to predict if someone is diabetes or not. And in that data set, you have like a 500 diabetes patient and also 500 non-diabetes patient. Wow, this is very balanced data. Nice one. So when you're going to divide, we need to divide this data now. If you add them together, it will become 1,000. If you divide them to 10 places, that means you are going to have 100 here, 100 here, 100. Each fold will be 100. The idea of stratification is that in the 100 that will belong to this first fold, you don't want to have 10 diabetes patients and 90 non-diabetes patients. You see, a data that was balanced before, but during your breakdown, you are creating imbalance. This is the idea of stratify. Stratify is saying that when you divide it into folds, you must make sure that the number of classes in each fold is equally the same. It might not be exactly the same. For example, if you have 500 data and 400 the other class, there's no magic you can do to make it equal, but at least one can be 10, another one 8, that's fine. But we don't want to have one is 10, another one is 1, or sometimes none is 0 actually. So in which case you have a fold whereby you don't have a particular class. So this is the idea of stratified cross validation. That when you are dividing the data within each fold, you also need to make sure that the number of each classes are equally the same as much as possible. This is the idea of stratified cross validation, just to avoid bias. Otherwise, it's going to be, because if you have a fold whereby there is 90 diabetes patient here, and there's only 90 non-diabetes patient, which is negative, and you have only 10 positive. But the next fold, unfortunately, you have 10 negative and 90 positive. We don't have this. Why creating this kind of imbalance is going to affect the model validation that you are trying to set up. So we take note of this as one way of doing that. Now, we have other special type of leave one out, like leave one out for validation. We're going to mention as some of the implications in the system we want to build. However, before we move on to the leave one out for validation and other options that are available, I want to show us practically how do we ensure, especially how do we do this particular tool, following some of the questions that I said we will receive on this. Now, so as usual, so I think we are all conversant with this. So you go straight without wasting time. You open the data set. So we have the program file there. We have the Weka. So we go to the data. So we can open an example data. Yeah. So this is our data set. This is where you make the big difference here. So we go to classify. Once the data is loaded, these are the partition option as provided for by the system. You can see here, if you're going for cross validation, this is the one we call the n-fold cross validation. You just select this option. And then you put the number of fold you want, 10. See, by default, you should implement stratify cross validation for people. That it makes sure that if your data is balanced before, we try to balance the classes when we divide it into 10. So you can also change this one to 3, as I said. You can also change it even to 5. So, however, like I said, 10 is what majority do. Once you select that, as we know, of course, you must have selected we want to use our friend, k-nearest neighbor. So We select k nearest neighbor. So we run the experiment. You see, this is the result of running for k or n fold cross validation. In the same way, I might want to use the other method, the holdout method I told us. So this is when you select the percentage split. It's now left to you. You now select the percentage here. My percentage split is going to be 70. I want to use 70. The default is 66. So it means the system is going to take 70% of data for training, and we automatically use the remaining 30% for testing. Yeah, so that means you are using this standard holdout method, which is division into only two partitions, training and testing set. So if you do that, you run it, so you're going to see the result here. This is the result of training and testing using 70% for training. Weaker will only show you the result of the testing set. What you are seeing here is the result of the 30% that you have allocated for evaluation, for the testing of the model. However, if you want it to show you the result of training, like I told us, the result of training is not not important, because if you get 100% in training, if you don't get good result in testing, it is useless actually. So that's why we're more interested in the testing outcome. So that's why Weaker gives you this. However, if you want Weaker to show you the result of your training, you can always go into one option and you can check it that, okay, output model for training. You can see, show me model for training. If you check this one, anytime you run your Weaker, it will give you the result of training procedure. Now, the question is then, what if I want to implement the partition into 3 for the holdout method? See, you want to implement that, what you can do, there are 2 or more ways for you to go by it. So the easiest way I recommend is for you to divide your data by yourself. First, in Excel, divide your data into 2, keep like 15% in a different file, Excel file. Keep it with you. You know now you're going to have 85% of your data in that Excel. Now upload that 85% into Weaker, which we did here. Upload it here when you open the file. Once you put it there, then come here and tell Weaker, now you have 85% of your data set, but now you have uploaded it to Weaker as a complete set. To you, it is 85%, but to Weaker, this is 100%. So you do the math now and tell Weaker what percentage of this data that I've uploaded to you should be used for training. So Weaker will go in, and so mathematician among us, if we have 85% of that data, we need the 70%, another 15%. Now, if you take it to 100, I think the new 15% now, if you take it to 100, that's going to be like, let's say 25% now. So you specified appropriately, because it was 85% total data set, 85%. Now it's become 100% to Weaker. So we need to specify to Weaker that, okay, this data with you now, use maybe 85% of this data for training, 85% of this data, 85. Which means it's going to use 15% of the present data that is loaded for testing. So once you run it, it will run the experiment and give you the result. So this is the result of training using only 15% of your data. Now, you now go and supply. You can see this option up here. You can see my mouse. You go up here, you click this supply test set. Since your model is built already, it has been built for you, and validation has been carried out using the second partition, which we call validation set. Now you now say supply test set. So the 15% that you kept inside one Excel file before, or text file, this is the place for you to supply it now. You now say, okay, select it. You now open the file. You go to your URL, wherever your file is located. Open this file. This file is going to be open for you. Okay, now you open the file. So that means you have gone inside and you brought in the 15% that you kept outside by yourself. Maybe it was just supplied by the company or the client you are working for. That is fine. Now the supply set is already provided. You just click start. It will run the experiment for you using this supply set. You can see. This is the idea of partitioning data into 3. This is how you can implement it in Weka easily. Another option also is if you don't want it to partition by itself, that's fine. You just say use training set, you supply the training set by yourself, see, which is the one you have uploaded here. You only upload 70% here. Then you now say supply testing set. You supply the first 15, which is for validation, and you can check the result. And then you supply the second one, and you can check the result. So these are two very easier ways that you can quickly implement holdout method in Weka without any, hopefully, any confusion or complexity. So by any of the methods just presented, you can easily check or evaluate your model to ensure that your model is actually performing to expectation. Because it's not just for you to train model, we want to be sure the model is going to perform when new data sets have been provided. So these are the two approved procedure because of time. So we're going to call it a day at this point and give room for any question or clarification that might arise. So once again, thank you and for listening.